Right now, there's a very high probability that the battery sitting under your hood is not actually dying. It hasn't suddenly lost its chemistry, it hasn't reached the end of its life cycle, and it definitely hasn't just given up overnight. In fact, in most cases, that battery is still holding the majority of its original capacity. It still has the stored energy, the chemical potential, and the ability to deliver power. But when you turn the key, the engine struggles. The starter hesitates, the lights dim, and within minutes, a mechanic is preparing to tell you that you need a $140 replacement. He hooks up a meter, sees a voltage drop under load, and immediately concludes the battery is bad, so you buy a new one. A fresh box of lead and acid replaces the old one, and for a while everything seems fixed. But what if the battery was never the problem? What if the real issue was something so small, so microscopic, that it never even showed up on the diagnostic tool? What's actually happening inside and around your battery is far more deceptive. Over time, a layer of crystallized lead sulfate forms on the internal plates. This is a natural byproduct of the chemical reactions inside a lead-acid battery, but that's only part of the story. On the outside, at the terminals where the electrical connection is made, another process is quietly taking place. Corrosion begins to build, lead dioxide interacting with environmental exposure, copper reacting with sulfur compounds, forming a crusty, often white or bluish layer. This buildup doesn't look like much, but electrically, it behaves like a barrier. It acts as a resistor. And resistance is the silent killer of performance in any electrical system. Here's the critical part most people never realize. Your battery can be full of stored energy, but if the current can't flow freely through the terminals and connections, your car behaves as if the battery is weak or dead. It's not a lack of power, it's a blockage of power. Think of it like a water pipe. The tank is full, but if the pipe is clogged, the flow slows to a trickle. That's exactly what this corrosion layer does. It chokes the electrical current before it ever reaches your starter motor. So when your mechanic tests the system and sees poor performance under load, he's not entirely wrong, but he's not seeing the full picture either. Now consider the scale of this misunderstanding. The global lead-acid battery market for vehicles generates over $58 billion every single year. Around 160 million car batteries are sold annually. That's not a small industry. That's a massive, deeply entrenched system built on repeat replacement. Batteries are expected to fail on a schedule every few years, like clockwork. But what if a significant portion of those replacements are happening not because the batteries are truly dead, but because of this resistance illusion? A simple layer of corrosion turning a healthy battery into a failed one. This is where the story takes a turn most people don't expect, because the solution to this problem is not some expensive tool, not a specialized chemical, and definitely not a new battery. It's something sitting in your kitchen right now, a common overlooked compound that costs virtually nothing. Baking soda, chemically known as sodium bicarbonate with the formula NaHCO3. Most people see it as a baking ingredient, something used for cakes or cleaning odors, but in reality it's a mild alkaline compound with a solution pH of around 8.3, making it highly effective at neutralizing acidic residues. And that's exactly what corrosion on battery terminals is, an acidic byproduct. When you introduce an alkaline substance like baking soda, it reacts with that acidic layer. It breaks it down, dissolves it, and removes the resistance that was blocking the current. In simple terms, it clears the pathway. The energy that was already inside the battery can finally flow freely again. No replacement needed, no expensive parts, just restored conductivity. This isn't theory. It's basic chemistry and electrical principles working together. The corrosion layer acts as a resistor, increasing resistance in the circuit. Ohm's law tells us that as resistance increases, current decreases, assuming voltage remains constant. Your starter motor needs a high current surge to turn the engine. If that current is restricted, the engine struggles or fails to start. Remove the resistance, and suddenly the same battery delivers the required current effortlessly. What makes this even more fascinating is that this concept isn't new. Long before modern automotive systems, engineers and craftsmen understood the importance of clean electrical and metal sunperk surfaces. The idea of removing oxidation and restoring conductivity goes back centuries. And in more modern contexts, this principle has been applied in high-stakes environments where reliability is critical. Because when systems fail, the first assumption isn't always that the power source is dead. It's that something is interfering with the flow. So the next time your car hesitates to start or your lights dim unexpectedly, it's worth asking a different question. Not, is my battery dead? But, is something preventing my battery from doing its job? Because in many cases, the answer isn't a $140 replacement. It's a microscopic layer of resistance that can be eliminated in minutes. And to understand why such a simple, nearly free solution isn't common knowledge, and why replacing the entire battery has become the default response, we need to go deeper. We need to look at what was discovered under extreme conditions, in environments where failure wasn't an option. because the truth behind this resistance illusion doesn't just explain your car's behavior. It reveals why a system worth billions depends on you never questioning it. Now, to understand why something as simple as an alkaline compound can restore what looks like a dead electrical system, you have to step far outside the modern auto shop and go back thousands of years, long before anyone knew what sodium bicarbonate was, long before chemistry had formulas, and long before anyone could explain pH, because the truth is, this isn't a new discovery, it's a rediscovered one. In the 2nd century, during the height of imperial Rome, engineers and blacksmiths were already facing a problem that looks almost identical to what's happening under your hood today. Bronze and copper components used in early communication systems, optical telegraph mechanisms and signaling devices would oxidize rapidly when exposed to air and moisture. This oxidation created a dull green or black layer that interfered with conductivity and bonding. Roman craftsmen didn't have the language of electrical resistance, but they understood the effect. Connections became unreliable, signals weakened, and mechanical efficiency dropped. Their solution came from wood ash. When wood burns, it leaves behind a residue rich in potassium carbonate, an alkaline compound. Roman blacksmiths would mix this ash with water to create a mildly alkaline solution, then use it to scrub and treat oxidized metal surfaces before soldering or reassembly. The result was immediate. The oxidation layer dissolved, the metal surface was restored, and conductivity improved. They didn't know the molecular interactions, but they knew the outcome. Alkaline cleaning brought metal back to life. Fast forward to the 16th century into the Safavid Empire, specifically the city of Isfahan, a global center of science, craftsmanship, and metallurgy. Here, master artisans were producing highly precise copper instruments, astrolabes, measurement tools, and early scientific devices. These instruments required clean, conductive surfaces to function accurately. But again, oxidation was the enemy. Copper exposed to air forms verdigris, the familiar green corrosion layer, which disrupts both appearance and performance. Safavid craftsmen turned to soda carbonate extracted from desert plants. This naturally occurring alkaline substance was processed and dissolved into cleaning solutions. When applied to oxidized copper, it reacted with the acidic corrosion layer, breaking it down and restoring the metal beneath. The process was repeatable, reliable, and became a standard part of instrument maintenance. No formulas, no lab analysis, just centuries of refined empirical knowledge, proving that alkaline solutions could reverse oxidation and restore function. At the same time, across West Africa, another remarkable tradition was evolving. In the empires of Mali and Songhai between the 12th and 16th centuries, Manda blacksmiths were developing advanced metallurgical techniques that impressed even visiting Europeans. These craftsmen used ash derived from millet and sorghum, again rich in alkaline compounds, to treat copper sunperk points in tools and early conductive systems. When Portuguese explorers encountered these methods, they noted something surprising. These alkaline treatments often outperformed the acid-based cleaning methods used in Europe at the time. That's a critical point. Across completely different civilizations, Rome, Persia, West Africa, the same principle kept appearing. Different materials, different cultures, different centuries, but the same outcome. Alkaline solutions removed oxidation and restored conductivity. They didn't share knowledge with each other. They didn't have modern chemistry. Yet they all arrived at the same conclusion through experience. If metal stops conducting properly, clean it with something alkaline. Now jump forward into the modern industrial age, specifically Japan during the Meiji era, 1868-1912. This was a period of rapid transformation. Japan was industrializing at an incredible pace, building telegraph networks, electrical systems, and early battery-powered infrastructure. But there was a problem. Imported maintenance chemicals were expensive and unreliable. Japan needed a standardized, low-cost, reproducible solution that could be used across the entire country. The answer was already known, just waiting to be formalized. Japanese technicians adopted and standardized the use of Tansan Suiso Natoriumu, sodium bicarbonate. What had once been an empirical trick became an official maintenance protocol. Telegraph operators, engineers, and technicians were trained to clean terminals and sunperk points using a simple baking soda solution. It was cheap, effective, and most importantly, consistent. That standard didn't disappear, it evolved. Even today, technicians working with major automotive manufacturers like Toyota and Nissan continue to use variations of this exact protocol when preparing vehicles that have been sitting in long-term storage. Before a car is delivered, before any battery is replaced, the terminals are inspected and cleaned, because the assumption isn't that the battery has failed, it's that something might be interfering with the connection. And then comes the most difficult piece to ignore, the hard data. During World War II, the United States military faced a massive logistical problem in the Pacific Theater. The environment was brutal. Extreme heat, relentless humidity, salt exposure, all of it accelerated corrosion at an alarming rate. Vehicle batteries were failing at 3 to 5 times the rate seen in Europe. Equipment that was supposed to last months was becoming unreliable in weeks. In 1943, the U.S. Army introduced a structured solution, Preventive Maintenance Program TPM-12. This wasn't guesswork. It was a standardized protocol implemented across units operating in these harsh conditions. One of its core requirements was simple: monthly cleaning of battery terminals using a baking soda solution. The results were tracked, recorded, and later declassified in 1971, and the numbers were not subtle. Units that followed the baking soda cleaning protocol saw a 42% reduction in battery replacements compared to units that relied on conventional cleaning methods. Not 5%, not 10%, 42%. Nearly half of the failed batteries didn't need to be replaced at all once the McCown layer was removed. Think about what that means. In one of the most demanding environments imaginable, under conditions where equipment failure could cost lives, the solution wasn't to replace batteries more frequently. It was to restore the connection, to eliminate resistance, to maintain conductivity. This is where the illusion starts to crack. Because when you line up the evidence, from Roman blacksmiths to Persian craftsmen, from African metallurgists to Japanese industrial standards, and finally to US military data, you start to see a pattern that's impossible to ignore. Across centuries and continents, the same principle keeps proving itself. When metal connections fail, it's often not because the power source is gone. It's because something is blocking the flow. And once you remove that blockage, the system comes back to life. So the real question isn't whether this works. History, industry, and military data have already answered that. The real question is why this knowledge, proven over thousands of years, is almost never the first solution you're offered today. Now we move from history and proof into the exact mechanism, the part that turns this from an interesting trick into something precise, measurable, and almost surgical. Because what's happening when baking soda touches that corrosion isn't just cleaning. It's a defined chemical reaction that was formally studied, documented, and optimized nearly a century ago. In 1928, chemical engineer Walter Rosenberg published one of the earliest Western technical analyses on electrical degradation in industrial systems. Working under the National Bureau of Standards, he was investigating why mine traction vehicles, heavy-duty electric machines operating in harsh, mineral-rich environments, were losing efficiency so rapidly. The issue wasn't battery failure in the traditional sense. It was connection failure. Terminals and sunperk points were accumulating acidic residues and oxidation layers that increased resistance and reduced current flow. Rosenberg didn't guess at a solution. He tested it, he measured it, and he established a repeatable, scientifically optimized ratio, approximately 50 grams of sodium bicarbonate per liter of water. That ratio created a solution strong enough to neutralize acidic buildup, but stable enough to avoid damaging the underlying metal. What he effectively did was take what ancient civilizations had discovered through trial and error and convert it into a controlled industrial protocol. Now, here's where it gets fascinating. What actually happens at the molecular level when this solution meets battery corrosion? A typical car battery operates using sulfuric acid. Over time, this acid interacts with the lead plates inside the battery and the metal at the terminals, producing compounds like lead sulfate and copper sulfate. These compounds don't just sit there harmlessly. They form crystalline, resistive layers that physically and electrically interfere with conductivity. They are, in effect, insulating the very connections that are supposed to carry current. When you introduce a baking soda solution, sodium bicarbonate with a pH of around 8.3, you're introducing a base into an acidic environment. And chemistry has a very clear rule for this. Acids and bases neutralize each other. But this isn't a slow, passive process. It's immediate, aggressive, and visible. The moment the alkaline bicarbonate solution contacts the acidic corrosion, a neutralization reaction begins. The bicarbonate ions react with the hydrogen ions from the acid. As they combine, they form water and release carbon dioxide gas. At the same time, the acidic compounds, like copper sulfate and degraded lead residues, begin to break apart. The rigid, crusty layer that was acting as a resistor loses its structure. It dissolves into water-soluble compounds that can be easily washed away. What you see during this process is something most people overlook, but is actually the clearest proof that the reaction is working. Bubbling, intense, rapid effervescence. That fizzing action is not just cleaning foam. It is literally carbon dioxide gas being released as the acid is neutralized in real time. Each bubble represents a microscopic reaction where acidity is being destroyed and converted into harmless byproducts. If you were to zoom in at a microscopic level, you would see the corrosion layer breaking apart, fragment by fragment. The beta that was blocking current flow is physically disintegrating. And as it disappears, the underlying metal, lead, copper, or Mishrit sunperk surfaces, is exposed again in a clean conductive state. The pathway for electrical current is restored, not by adding energy, but by removing resistance. This is where the intelligence of the process becomes undeniable. You're not boosting the battery. You're not recharging it in some mysterious way. You're restoring the conditions that allow it to function as it was originally designed. It's a correction, not an enhancement. And that distinction matters because it explains why the results can feel so dramatic. The battery didn't gain new power. It regained access to the power it already had. Now step back and look at the financial side of this reaction, because this is where the contrast becomes almost absurd. A standard 200-gram box of food-grade baking soda typically costs somewhere between 40 and 80 cents, depending on where you buy it. From that box, you're using roughly 2 tablespoons for this process. That translates to a cost of about 1 cent per treatment. 1 cent to perform a reaction that dissolves corrosion, restores conductivity, and can bring a struggling electrical system back to life within minutes. Now compare that to what happens at a dealership or service center. If they offer a battery terminal cleaning and conditioning service, the price usually falls between $45 and $90. And in many cases, that service is either skipped entirely or treated as secondary to the main recommendation, replacing the battery. That replacement typically costs around $140, sometimes more depending on the vehicle. So what are you actually paying for? In many scenarios, you're paying for the outcome of a 1 cent chemical reaction. Not because the chemistry is expensive, not because the process is complex, but because the underlying cause, the resistance layer, is rarely presented as the primary issue. And this is where everything connects. The ancient methods, the industrial standardization, the military data, and now the chemistry itself all point to the same conclusion. The failure you're experiencing is often not a failure of capacity. It's a failure of conductivity. And conductivity can be restored with a reaction so simple, so well understood, and so inexpensive that it almost feels like it shouldn't work. But it does. Not because it's a trick, and not because it's a hack. It works because it's chemistry doing exactly what chemistry has always done, neutralizing, dissolving, and clearing the path for energy to flow. Now we bring everything together into a precise, foolproof system you can execute in your own driveway in under 5 minutes. This is not theory anymore. This is the exact protocol. The same logic used across industrial systems, refined into a simple routine anyone can follow. And if you follow it correctly, you're not just cleaning your battery, you're restoring the electrical pathway your entire vehicle depends on. Start with sourcing the compound. You don't need anything specialized, and you definitely don't need to buy expensive automotive chemicals. Standard food-grade baking soda, sodium bicarbonate, is exactly what you want. The same box sitting in your kitchen cabinet is chemically identical to what's used in industrial and maintenance settings. There is no advantage to lab-grade material for this application. What matters is consistency and proper mixing. For the mixture, dissolve 2 tablespoons, roughly 30 grams, of baking soda into half a liter of hot water. Ideally, the water temperature should be in the range of 140 to 160 degrees Fahrenheit, or about 60 to 70 degrees Celsius. The reason for using hot water is simple but important. Higher temperature increases the dissolution rate, meaning the baking soda fully integrates into the water more quickly and evenly. It also slightly accelerates the chemical activity when applied. If you only have room temperature water, the process will still work, but it will be slower and slightly less aggressive. Stir the solution thoroughly until there are no visible particles left. You want a fully dissolved, uniform liquid. Before you touch the battery, there's one step that is absolutely critical. And this is where most people make dangerous mistakes if they skip it. You must disconnect the battery terminals in the correct order. Always start with the negative terminal. This is the black cable marked with a minus sign. Remove it first. Then move to the positive terminal, the red cable marked with a plus sign. This sequence is not optional. It prevents accidental short circuits. If you were to remove the positive terminal first and your tool accidentally touched a grounded metal part of the car, you could create a direct short. By removing the negative first, you eliminate that risk. Make sure you're working in a ventilated area. While most modern batteries are sealed, they can still release trace amounts of hydrogen gas, especially if they've been recently charged or are under stress. You don't need to panic, but basic ventilation is a smart precaution. Now comes the actual application. Take an old toothbrush or a small stiff bristle brush and dip it into your baking soda solution. Apply it directly onto the battery terminals and the Andrews surfaces of the cable clamps. The moment the solution touches the corrosion, you'll see it, the bubbling reaction. This is the effervescence you learned about earlier. That fizzing is the acid being neutralized in real time. Start scrubbing gently but thoroughly. You don't need excessive force. Let the chemistry do the work. Focus on the sunperk points where metal meets metal. These are the areas where resistance matters most. Continue brushing for about 30 to 90 seconds. Watch the reaction closely. If the bubbling is intense, it means there was significant acidic buildup. Once the bubbling begins to slow or stop, that's your signal that most of the active corrosion has been neutralized. If the initial reaction was very strong, apply a second round of solution and repeat the process. After the scrubbing is complete, rinse everything thoroughly with clean water. This step is important because it removes the dissolved compounds that were just broken down. You don't want those residues sitting on the surface. Once rinsed, dry the terminals completely using a clean cloth, or, if available, compressed air. The goal is to leave the metal clean, exposed, and completely dry. Now comes the step that almost nobody talks about. But it's the difference between a temporary fix and a long-term solution. Once the metal is clean, it is also vulnerable. Bare metal exposed to air, moisture, and battery acid vapor will begin to oxidize again. That's where you create a protective barrier. Apply a thin, even layer of petroleum jelly, commonly known as Vaseline, or use white lithium grease or dielectric grease if you have it. Spread it directly onto the battery posts and inside the cable clamps. This layer doesn't interfere with conductivity. Instead, it seals the surface from Hawa and moisture, dramatically slowing down the corrosion process. Think of it as insulation against future resistance buildup. With the barrier in place, reconnect the terminals, but this time in reverse order. Start with the positive terminal first, then connect the negative terminal last. Tighten the clamps securely, but do not over-tighten. Battery terminals are made of lead, which is a relatively soft metal. Excessive force can crack the terminal post, turning a simple maintenance task into a costly repair. Once everything is connected, start the vehicle and let it run for about 15 minutes. This allows the alternator to fully charge the battery and stabilize the electrical system. In many cases, you'll notice the difference immediately. Faster cranking, stronger ignition, brighter lights. Not because you added power, but because you removed the resistance that was blocking it. Now, consider the long-term impact. A standard mid-range lead-acid battery is typically expected to last around 4 to 5 years under normal conditions. That's the industry baseline. But when you consistently remove corrosion and maintain clean, low-resistance connections, you reduce stress on the battery. You allow it to operate efficiently. And that alone can extend its lifespan to 7 or even 8 years of service. And this is where it all comes full circle. Because what you just did, this 5-minute, 1-cent protocol, is something most people are never taught. Not because it doesn't work, but because it shifts the entire narrative from replacement to restoration. So here's what comes next. Subscribe right now, because in the next video, we are exposing the $2 Japanese liquid that permanently protects your aluminum engine block from corroding from the inside out. A compound your repair shop desperately hopes you never find. You don't want to miss it.